Now, I would like to explain the green function. A green function is not a special function like an exponential function or a trigonometric function. In general, it is a function used to solve a differential equation. So the form of the green function depends on the differential equation we want to solve. In the present problem, the equation to be solved is this one-dimensional Helmholtz equation for the vector potential A sub z. We define the green function so that it satisfies the corresponding equation with a delta function on the right-hand side. This is called the green function problem. The green function depends on x and x prime. Here, x prime represents the position of a unit source, so the green function represents the response when a unit source is located at x prime. If the green function is known, the solution of the original problem is obtained by multiplying it by the source term and integrating over all source positions. In this way, solving the original problem is reduced to finding the green function. Next, let me explain why this integral formula really gives the desired vector potential. We compute the right-hand side and check whether it reproduces the vector potential generated this source. Because the source term is minus mu j sub z, we can replace it by the left-hand side of the original Helmholtz equation. Then, by integrating by parts twice and using the fact that both the vector potential and the green function vanish at infinity, we can move the derivatives from a sub z to the green function. This property, that the operator can be moved in this way, is called self-adjointness. An operator with this property is called a self-adjoint operator. For details, please refer to Supplemental Movie 1. Also, the green function has the reciprocity. Please refer to Supplement 2. Using this property, the term in parentheses becomes exactly the left-hand side of the green function equation. Therefore, it is replaced by minus delta of x prime minus x. Applying the delta function, we finally obtain the vector potential. Therefore, it follows that this expression is indeed the vector potential. Now let us actually determine the green function. The equation contains a delta function, which makes it difficult to solve directly. So we first consider the region where x is not equal to x prime. In that region, the delta function is 0, and the equation becomes a homogeneous Helmholtz equation. Its general solution is a linear combination of two exponential functions. The first term corresponds to the wave propagating in the minus x direction, while the second term corresponds to the wave propagating in the plus x direction. So, the physical interpretation tells us which wave should be chosen in each region. There is a source at x equals x prime, so the solution must describe waves propagating away from that source. For x less than x prime, the wave propagates in the minus x direction. For x greater than x prime, the wave propagates in the plus x direction. Therefore, the green function has one form on the left side of the source and another form on the right side. The constants are determined by two conditions. First, the green function itself is continuous at x equals x prime. This means that the values from the left and from the right must be equal there. Second, the first derivative is discontinuous. To find the size of the jump, we integrate the green function equation over a very small interval containing x prime. The integral of the second derivative is simply the difference of the first derivative at the endpoint. The right-hand side is the integration of the green function. The result is readily obtained and equals -1. Now we take the limit of a vanishing interval. The first and the second terms of the right-hand side give the difference of the first derivative across the source point. The third terms, the integral of the green function term, becomes 0 in the limit of a vanishing interval. As a result, we obtain the jump condition for the first derivative. Substituting the two waveforms give another relation of the two coefficients. Combining this condition with the continuity condition, we can solve for the two coefficients. Then, substituting them back, we obtain the green function in explicit form. Equivalently, it can be written in a compact form using the absolute value of x minus x prime. Finally, let me summarize the green function method. The problem we want to solve is the one-dimensional Helmholtz equation for the vector potential, together with the boundary condition that the vector potential goes to 0 as x goes to plus or minus infinity. To solve this problem, we first introduce the green function. The green function is defined as the solution of the corresponding equation with a delta function on the right-hand side, and with the same boundary condition at infinity. By solving this green function equation, we obtain the green function explicitly as this equation. Once the green function is known, the vector potential can be written as the integral of the green function multiplied by the source current density, J sub z. This is explicitly given by this equation. In this way, the original differential equation is reduced to an integral representation using the green function. This is the basic idea of the green function method. The green function gives the response to a unit point source, and we superpose those responses to construct the solution for an arbitrary source distribution.